So last time we talked all about the hardware foundations of the ARM Cortex-M processor. But even the most amazing hardware is basically just a fancy rock until you have the software to make it sing. And for embedded systems, that software requires a very specific approach. There's a saying that good software on average hardware will always beat average software on good hardware. So today, we're going to dive into the art of crafting that high-quality embedded software.
We'll kick things off with the most important piece of the puzzle, having the right mindset. From there, we'll get into the nitty-gritty of code craftsmanship and how to build a solid modular architecture. Then, we'll look at some really cool ways to model system behavior, manage multiple tasks at once, and finally, how to handle our resources and actually verify that our system works the way it's supposed to. Let's get into it.
Okay, before we even think about writing a single line of code, we have to talk about attitude. Seriously, if you're coming from desktop or web development, you might be used to pushing a feature and fixing bugs later. But in the embedded world, we're talking cars, medical devices, industrial control. That just doesn't fly. Failure is not an option. So the absolute #1 rule, the foundation of everything, is reliability over features.
Now, let that sink in for a second. This isn't about shipping an unfinished product. It's about building a rock-solid core. If you can guarantee that a few key functions are absolutely 100% bulletproof, you can build everything else on that with confidence. A system that works predictably, even if it has fewer bells and whistles, is infinitely more valuable than a feature-packed system that's buggy. This one idea shapes every single decision we make from here on out. With that mindset locked in, let's talk about the actual craft of writing code. You have to remember, your code really has two audiences. The first is the compiler, and frankly, it doesn't care if your code is pretty. The second and more important audience is other human beings, and that includes you 6 months from now. So writing for humans is all about making your code clear, consistent, and easy to maintain. Just look at this example here. On the left, we've got int temp. Okay, what kind of integer is it? Is it signed? How big is it? And process function. Process what? It's totally ambiguous. But now look at the right. UINT temperature sensor tells us everything. It's an 8-bit unsigned integer, it's a global variable, and it holds a temperature reading. Same for the function, ADC process sensor data. It's perfectly clear. This is what we mean by self-documenting code, and it saves so much headache down the road. And that leads us to a really powerful design principle, separating policy from mechanism. Think of it like this. The policy is the public promise of what your function does. This goes in the header file, where anyone using your code can see it. But the mechanism, all the messy details of how it gets the job done, that stays hidden away in the source file. It's only for the person who needs to maintain it. This separation is the heart of good abstraction. It's how we build really complex systems without getting lost in the weeds.
So, how do we take these ideas and scale them up for a big project? Well, the absolute worst thing you can do is write one gigantic, tangled mess of code. The key is to break it down. Modular architecture is all about designing your system as a collection of independent, interchangeable building blocks. It is your #1 weapon against complexity.
A really common and really effective way to organize these blocks is in a layered architecture. At the very bottom, you've got the board support package, or BSP. This is the code that knows all the tiny details about your specific microcontroller. Then, sitting on top of that are the device drivers, which give you a nice, clean way to talk to peripherals. And finally, at the top is your application logic, the code that actually solves the user's problem. And the beauty of this, if you need to switch to a different microcontroller, you just change the BSP. The rest of your code doesn't even have to know.
So what exactly is a device driver? Well, think of it as a translator. It takes a simple, high-level command from your application and translates it into all the complicated, low-level bit twiddling needed to make a piece of hardware work. So instead of your main code having to manually flip 5 different registers just to put a character on an LCD screen, you just make a simple call, like LCD print string. The driver handles all the dirty work for you, hiding that complexity. Okay. So we've structured our code into these nice, clean modules. But how do we manage its behavior over time, especially when it has to react to a bunch of different events? One of the most powerful tools for this is the Finite State Machine, or FSM. It's just a formal way to design a system that can only be in one of a few specific states at any given moment. And the concept is really simple. You can see here, the circles represent the different states the system can be in. Think of a vending machine. It can be idle, accepting coins, or dispensing.
The arrows are the transitions. An event, like you putting in a quarter, causes the machine to transition from the idle state to the accepting coin state. Using a state machine makes your system's behavior totally predictable and way, way easier to debug than a giant tangled mess of if-else statements. All right, now things start to get really fun. Most embedded systems feel like they're doing a bunch of things at the same time, monitoring a sensor, updating a display, listening for a button press. But a single core processor can only do one thing at a time. So how do we create the illusion of doing multiple things concurrently? This is where we get into the idea of threads.
The classic way to do this is with a foreground/background system. The foreground thread is just your main program, chugging along in an infinite loop. Think of this as you sitting down to read a book. It's a predictable, sequential task. The background thread is an interrupt service routine, or ISR. This is triggered by some hardware event, like data arriving from a sensor. This is like your phone ringing. What do? You immediately put a bookmark in your book, you answer the phone, and when the call is over, you go right back to reading exactly where you left off.
But wait, this creates a new problem. Now that we have these two things running in different contexts, how do they talk to each other safely? What happens if the phone keeps ringing? If the fast interrupt is generating data way faster than your main loop can read it? Just using a global variable is a recipe for disaster. You'll lose data. The classic solution is a buffer, specifically a first-in, first-out queue, or FIFO.
The best way to picture a FIFO is like a conveyor belt. The ISR is the producer. When new data arrives, it quickly shoves it onto the back of the belt and immediately gets back to its important work. The main loop is the consumer. Whenever it has a free moment, it walks over to the front of the belt, grabs the oldest piece of data, and processes it. This FIFO acts like a shock absorber, completely decoupling the producer from the consumer and making sure no data gets lost and everything is processed in the right order.
We're almost there. We have a nearly complete picture of how to design our software, but there are two final, absolutely critical topics we have to cover. First, managing our very limited resources, especially memory. And second, something that should never, ever be an afterthought, the process of verifying that our system actually works. In other words, debugging. Okay, listen up, because this is important. In many embedded systems, especially ones that have to run for months or years without a reboot, using dynamic memory, things like malloc and free, is playing with fire. Why? Because of a nasty problem called heap fragmentation. Imagine your memory is a big block of Swiss cheese. Every time you allocate and free memory, you're poking holes in the cheese. Eventually, you might have enough total free space, but it's all in tiny little disconnected holes. So when you ask for one big chunk, the allocation fails and your system crashes. And finally, verification. Debugging isn't just about reacting to problems. It's about proactively proving your design is correct. A monitor lets you peek at variables in real time without stopping the system. A heartbeat, like a simple blinking LED, is an invaluable gut check to see if your processor is even alive. Performance profiling is crucial for proving that your tasks meet their deadlines. And a system dump can take a snapshot of everything right before a crash, letting you figure out what went wrong later. These aren't just add-ons, they are essential design tools.
So let's recap. We've gone from the core mindset of reliability to the craft of writing clean code. We know how to build a layered architecture, manage complex behavior with state machines, and handle multiple tasks using threads and queues. We've even talked about managing memory safely and verifying our logic. But there's still one big piece of the puzzle missing. It's not enough for our software to just be logically correct. In the real world, it also has to be temporally correct. So the big question now is, how do we guarantee our software actions happen at the exact right moment? That's the challenge we're going to tackle next time.